Okay, second half of lesson 10.3. We're looking at ways to prove that a quadrilateral is a parallelogram. We're going to come up with 6 different ways. So think about those 6 ways right now. Pause the video, write them down, and then you'll see them in just a moment. All right, so here's all 6 of the ways to prove that a quadrilateral is in fact a parallelogram. Okay, one of these is a definition. So one of these is automatically biconditional. Okay, we always know the definitions are biconditional. Biconditional just means we can write it in both directions. In this case, what we're looking for is first properties, and then once we have certain properties, we can say that based on these properties, we do have a parallelogram. Okay, and then one of these is a definition, and the definition here is number 3. Okay, so this is the definition of a parallelogram. So it's good to just be able to distinguish what's the difference between the definition of a figure versus properties that are just outcomes of that definition. So we would be able to take this definition here in number 3, and we'd be able to say, okay, well, if we know that both pairs of opposite sides are parallel, we know that we have a parallelogram. But also we would just be able to say that if we have a parallelogram, then we know that both pairs of opposite sides are going to be parallel. Now, based on this definition, we'd be able to learn all of the other additional properties of a parallelogram. Okay? The other 5 if-then statements that are here are not properties of a parallelogram. These are ways to prove a parallelogram. You have a whole nother set of properties that starts with, if the quadrilateral is a parallelogram, then some property is true. Okay, so do make sure that you're thinking about the order of the if-then. And sometimes you'd be able to flip them around, and sometimes you can't, okay? But always you can reverse the definition, because the definition is always what we call biconditional, okay? So now for problem number 4, we have to take these 4 points here. We can see that these 4 points are in 3D, and we want to show that the quadrilateral is a parallelogram. So we get to choose any one of these 6. Doesn't matter which one you choose. You can choose your favorite one out of these 6. Some of them are impossible to prove using what we have. Some of them are going to be longer to prove. Some of them are going to be shorter to prove. You might just remember one better than the other. Whether it takes more work or less work, pick it if you know that it works to prove that your quadrilateral is in fact a parallelogram. Okay, so let's think about how could we take these points and using what we know, think about what we know about vectors, think about what you know about parallel, think about what you know about congruent and how you could show either parallel or congruent using vectors. All right, so in choosing which one of these 6 methods you want to do, you can think about what you know about congruent, about what you know about parallel, and what you know about angles in 3D. So if we choose the first one, both pairs of opposite sides are congruent, then we need to do 4 calculations to get the length of each of the 4 sides, and we can do that using either distance formula, or we can write vectors for each of the sides and then calculate the magnitude. The second one here, if one angle is supplementary to both adjacent angles, we have the angle between 2 vectors formula for 3D. So we can find the angle between 2 sets of adjacent angles, and we can calculate to make sure that those are supplementary. Number 3 here, if both pairs of opposite sides are parallel, we know that we can determine if vectors are parallel, and so we could find a vector to represent each of the 4 sides, and then check to make sure that they are scalar multiples of each other. Number 4, both pairs of opposite angles are congruent. Again, we would need to find the angle between 2 vectors for all 4 of the angles and verify that they are the same. If one pair of opposite sides is both parallel and congruent, choose one set of sides, either calculate distance formula and magnitude, and then calculate the vectors to make sure that they are parallel. And then last, number 6, if the diagonals bisect each other, we can find each of the 2 diagonals and calculate the midpoint of each diagonal and verify that the midpoint is going to be the same. So you can choose whichever one you would like to do based on whether you think it's going to be easier, harder, more work, less work, or it's just the property that you remember. and show the calculation for that. Remember, this is a show problem. So that means it's like a proof. So that means you must write down every little tiny thing. Make sure you keep everything labeled, okay? Also, I want you guys all to notice, this is very, very important. It says show that quadrilateral ABCD is a parallelogram. So you know that it goes in the order of A, B, C, and D. So I would recommend drawing a little sketch of the diagram, okay? So A, B, C, D. I'm not actually graphing it, but I know that it goes in this order. So if I'm finding opposite sides, I will know that AB is opposite CD. And I also know that BC is opposite AD. Now, in some cases, you might not be told the order of the letters. Do not assume it goes in alphabetical order, because it's not always true, okay? So sometimes what you will need to do is you will need to look at the numbers of the points, and either you're graphing those points or doing your best to graph those points, which I know graphing 3D and figuring out what's where is a little bit tricky, but there will be enough information given that they have certain points have a common X value or a common Y value. So you know that they're kind of across from each other, up and down from each other. So you're going to look at those and interpret that information to be able to figure out which order the letters go in. Okay? So you're working on choosing one of these 6 and proving it on your own. All right, so I chose option number 1 to prove that both pairs of opposite sides are congruent. So calculating the magnitudes or the lengths in 2 different ways. So one by actually calculating distance formula, you get AB is square root of 29, CD is square root of 29. We know that those are opposite, so that means that they are congruent. And then calculating, first of all, calculating BC. And so here we have the vector BC using what we know about how to find a vector given 2 points. And then we find the magnitude of BC, and we get the magnitude of BC is 1. And similarly, we do the same with AD. And so we get vector AD, then we find the magnitude of AD, and we also get 1. So what we've shown is that we've shown that both pairs of opposite sides are congruent, and therefore we're going to have a parallelogram. So at the end of the first pair of opposite sides, put a little statement. So therefore, AB is congruent to CD. Okay, so interpret that calculation, and we can write that statement. And then we're going to do the same thing with the other pair of opposite sides. So at the conclusion of the second pair of opposite sides, which I did vectors, you could do all vectors, you could do all distance formula, whatever you choose. And we would say, therefore, BC is congruent to AD. Okay? And then the final thing that you need to do is summarize your final answer. So it asks you to show that quadrilateral ABCD is a parallelogram. Okay? So your final statement then is going to be the if-then statement that we talked about earlier. So you're going to say if both pair of opposite sides are congruent, then parallelogram. Okay? So you kind of have 3 different parts to this. You have your first calculation, set of calculations, in a conclusion, your second set of calculations with its conclusion, and then we have our both pair of opposite sides are congruent, then we have a parallelogram. But you have one pair statement, second pair statement, and then the final statement. Okay? And again, if you chose one of the other methods, that's perfectly fine. So if you did both pairs of opposite sides are parallel, and you have your vectors and your scalar multiples, at the end of your calculations for the scalar multiples, you say, this vector is a scalar multiple of that vector, therefore AB is parallel to CD. Okay, so you interpret that within what you're doing. All right, so next part, finding this area. We want to find the magnitude of the cross product, and we have to make sure that we have 2 adjacent sides. So again, this is where it's really important to know what order the letters go in. If it goes A, B, C, D, if it goes A, C, D, B, which order the letters go in so that you're choosing the appropriate adjacent sides. So if it doesn't tell you, you need to make sure that you are thinking about the graph and where those points will be located to figure out which sides are adjacent. All right, so we know how to find a cross product. So to do the cross product, we're going to use the determinate method that we learned from chapter 7. Okay? So using that determinate method, let's go ahead and let's find this cross product. So finding the area of A, B, C, D, we need two adjacent sides, okay? Well, let's choose one of the vectors that we already calculated. Let's see, we already calculated BC. So I know that vector BC is 0, 1, 0. So if I'm going to choose vector BC, then I need to choose another vector that's adjacent to that. So if I choose BC, let's go ahead and also choose BA. And those are two adjacent vectors. So let's go ahead and calculate vector BA. So vector BA means I'm going to take the A point minus the B point. So I have 3 minus 1 is 2. And you don't have to show 3 minus 1. You can just do that in your head. Okay? So A point minus B point, 3 minus 1. 5 minus 2 is 3. 0 minus 4 is negative 4. And now we're going to calculate the cross product. So remembering what you know about cross product, go ahead and calculate your cross product. And so we're calculating the area. So I'm just going to write this down with saying what I'm doing. So the area of A, B, C, D is going to equal the magnitude of the cross product, not of U cross V, but of BC cross BA. So I'm saying what I'm going to do. And so now let's go ahead and calculate the cross product. If you want to do the cross product on the side. So BC cross BA. So I'm setting it up like a determinant. My first row is the I, J, K. And then my second row is vector BC, which is 0, 1, 0. And my third row is vector BA, 2, 3, negative 4. So go ahead and pause and calculate your cross product. All right, so you calculated your cross product. You should have a cross product for these two vectors of negative 4, 0, negative 2. If you chose two different vectors, your cross product might look a little different. But regardless, once you find your magnitude here, now we're going to take that cross product, put it into the magnitude. And when you calculate, you're going to show your work for your magnitude. And when you calculate that, your magnitude is... All right, so we have 2 square root of 5, and remember that this is an area. So the area of A, B, C, D then is 2 square root of 5 units squared. Don't forget to put units, even though there's no specific unit like centimeters, feet, meters, things like that. Still put units squared so that you're showing that you're understanding what the area units are, that they're squared units. Okay? All right, so now we're going to go on to part C. We need to determine whether ABCD is a rectangle. So we know that ABCD is a parallelogram. So we want to think about what's the quickest way to show that something that you already know is a parallelogram is also then going to be a rectangle. So all we need is one angle, because if one angle is a right angle, because of the supplementary properties of parallel lines, then that means all 4 angles would be right angles. And the definition of a rectangle is a quadrilateral with 4 right angles. You might think, well, couldn't it be also a square? It could be, but it doesn't have to be. So if you know that all 4 angles are right angles, then you know for sure it's a rectangle. You could prove all pairs of sides are congruent to then say that it's a square, but 4 right angles means for sure rectangle. But if it's already a parallelogram, all you need is 1 right angle. So now we think about how can we prove that there is 1 right angle, and I want us to do this using vectors. So we have 2 adjacent vectors that we've already used. We have vectors vectors BC and BA. So what would we have to do, or what could we do with those 2 vectors to prove that we have a right angle? So first method, find the angle between 2 vectors, right? Use the cosine theta formula to find the angle between 2 vectors, but there's a quicker way. So the quicker way is to find the dot product. The dot product, if the dot product is equal to 0, then the 2 vectors are orthogonal. And we know that orthogonal means that they are going to be perpendicular. So orthogonal, perpendicular, dot product equals 0 means orthogonal. So let's go ahead and find the dot product of, we have to use 2 adjacent vectors. So let's use the same 2 that we have, BC and BA. So calculating BC dot BA. So vector BC dot vector BA, and we want to see what that is. So go ahead and do the calculation. All right, so you should calculate your dot product to be 3, and of course you'd show your work for that. And so then we can say that ABCD blank, so is or is not, a rectangle, because the dot product of two adjacent vectors is or is not equal to 0. So in this one, ABCD, well, we know that this is not equal to 0, right? So if it's not equal to 0, it means it's not perpendicular. Let's put that conclusion here as well. Therefore, not perpendicular. You can write out the word orthogonal too. And so that means that it is not a rectangle. And yes, interpreting this right there, include that as well. Okay, so you're saying, I found the dot product equals 3. What is the conclusion of that number? The conclusion of that number is that the two vectors of the two sides are not perpendicular or not orthogonal, which then means that ABCD is not a rectangle. Okay? All right. So we're going to finish up with just 2 more applications of dot product and cross products. So we already know how to find dot products, and we also know how to find cross products. So here we have defined as what we call the triple scalar product, or you can abbreviate it TSP. So triple scalar product here you can see is a dot product and it's a cross product. Okay, so it's going to be given these 3 vectors u, v, and w, u dot v cross w. You can of course calculate that by doing the cross product of v and w, and you could say, okay, well, I'll do the cross product of this. You do that by doing a determinant, and then you take that vector and you dot it with u. You could do that and do that in 2 steps. But what works out is that that calculation of those 2 different things can just be one determinant set up in this way. So you have whatever the first vector is, that's your row 1. The second vector is your row 2. The third vector is your row 3. And that's it. And you just go ahead and you calculate using those numbers. Okay? So let's just go ahead and do this one. Triple scalar product. So we're finding this determinant. So triple scalar product is going to be technically u, stop moving, u dot v cross w. And so our vector u is row 1. So we have 2, 3, 3. Our vector v is row 2, 4, 4, 0, and vector w is row 3, 0, 0, 4. And so now we're going to calculate our 3 by 3 determinant. We're not looking for the cross product here, so we don't have the ijk row that we have to choose. So you can choose any row or any column that you would like to calculate the determinant. So which row or column would be the best one? Last one, row 3. Because it has the most zeros. If you don't choose row 3, no big deal. Okay, but row 3 is going to be the one that's going to be the least amount of calculation, the least amount of work, because it has 2 zeros in it. And you're going to multiply those first 2 terms by a 0, so those first 2 terms are going to equal 0. Okay, so go ahead and calculate your triple scalar product using that determinant. All right, so here we can see that we have negative 16 for an answer. Okay, there's a little bit of the remnants of the work. Choosing 0, 0, 4 means we're going to have this 0 is a multiplier here, this 0 is a multiplier there, this 4 is the multiplier here, and then we do our 2 by 2 determinants for each of the terms in between. So we move across, and for the first term, we eliminated column 1, second term we eliminated column 2, last term we eliminated column 3, and then we did the 2 by 2, so we did 2 times 4 is 8, minus 3 times 4 is 12. That's the last term that really matters. Okay? You may or may not have thought about it. Hopefully you did. But because of the zeros, you still could have ended up with the right answer without thinking about it. Remember that this last row is plus minus plus. Okay? So don't forget that sign change rule. Okay? So we have our plus, we have our minus, and we have our plus. Okay? One more application of cross products. Geometric property. Oh, go back to the blank one. Geometric property of the triple scalar product. Okay, and there's a little diagram there that kind of shows you a little bit more of where this comes from. So we have our triple scalar product again, and this just says that the volume of this is a fun word, parallelepiped. Say that 20 times in a row. Parallelepiped, 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 parallelepiped. It's so fun. The volume of a parallelepiped. So this could also be the volume of a box, a rectangular prism. A parallelepiped is really just like a box that's slanted. Okay, so you can kind of think about that just to get a visual of it. And this says that if we take the triple scalar product for, again, adjacent edges, so they all have to come from one vertex. So one vertex, one vertex, one vertex. So you have to make sure you're coming from one vertex and that they are representing sides. Don't make a diagonal. So again, it's important to know the structure based on the letters, okay? So you can use this geometric property to find the volume of a parallelepiped, okay? That's just a property. Apparently, the next problem doesn't have anything to do with that. Okay, so continuing with this problem here we're asked to find the area of a triangle, okay? And so I want you to notice over here that the diagram shows that the area of the base of this parallelepiped is the magnitude of V cross W. And so if we want to find the area of a triangle, essentially what we could think about is we're going to take that parallelogram and we're going to cut it in half. Okay, so the area of the triangle is going to be half of the area of the parallelogram. So the area of the triangle is half the area of the parallelogram. And the area of the parallelogram is going to be the magnitude of, and we can think about our triangle here, triangle ABC. So we would need the magnitude of AB cross, let's say, BC, okay? And we're just going to calculate the cross product of AB and BC, and then we will be able to find our magnitude there. I apologize, I'm going to change this BC. Instead, I'm going to do AB cross AC. So let's do AB cross AC. Go ahead and pause the video, calculate the cross product, multiply it by 1/2. And let me add also in here, I forgot one thing. I'm going to put a plus or minus. Nope, I don't need that actually. Never mind. We're all good to go. So calculate the cross product, pause the video, and then check your answer. All right, so here's what you should have found, that AB cross AC is going to give us the vector -6i plus 6j plus 18k. And we find the magnitude of that, and we get 6 square root of 11. And then we find half of that, and we get 3 square root of 11 units squared. Thank you, and please let me know if you have any questions.